The item is emulating Mersenne Twister with Cellular Automata. I think Kamalika Bhattacharjee will be the speaker. Yes, please.
Yes.
I invite Kamalika Bhattacharjee, please.
Yes, thank you, sir. Yes, you must speak.
Yes, please start.
Okay, so thank you for giving me this opportunity. This paper, emulating Mersenne Twister using Cellular Automata. This is a work basically done by my graduate students Nitin, Shobhit, and Nikhil at the Department of Computer Science and Engineering, NIT Trichy. First, I will talk about what is a PRNG. Then I will move to Mersenne Twister and the work. A PRNG is a pseudo-random number generator, that is called PRNG. Pseudo-random numbers and some numbers which appear to be random but are reproducible or new. So reproducibility comes from the background algorithm, which are called the pseudo-random number generators. By definition, we can write a pseudo-random number generator as a structure of 5 tuples, where the first tuple is S, the finite set of states. Second is mu, the probability distribution over the seed. F is the state transition function. U is the output space, and G is the output function. So the generator will take a seed S0, which is part of the finite set of states based on mu, and continue generating numbers based on the output function. And at each step, the next state will be updated based on F. Now we have, for every PRNG, we have a period, because it is a finite state machine. The starting state will come after some time. So the length after which the starting state comes back, that is the period. And period is the most important thing in a pseudo-random number generator. There are several properties which a good PRNG needs to satisfy. These are some of them, and there are mainly 3 classes of PRNGs: linear congruential generators, also called LCGs, linear feedback shift register based generators, and cellular automata based generators. Here we are talking about Mersenne Twister. Mersenne Twister is a LFSR based generator. It is a variant of twisted generalized feedback shift register, which has the recurrence relation of this type, and its facility is it avoids, in its implementation, it avoids multiplication, divisions, uses cache pipelines to efficiently use the memory, which makes it very fast. The popular variant of Mersenne Twister is MT19937. This 19937 comes from the period length of it, which is a Mersenne prime 2 to the power 19937 minus 1. It needs 624 words for working, and it will take a 32-bit seed. Now you might wonder that how 32-bit seed will work on a recurrence which has a size of 19937. Now, if you observe, if we take 32 cross 624, that is basically 19936. So the length of the Mersenne prime, that is the recurrence, has this facility that it has the form of 32 cross 624 plus 1. And when we are taking the 32-bit seed, that seed will be used to fill up the whole space first. After that, it will keep on generating the next ones. For this MT19937, there are 2 versions. One is 32-bit, another is 64-bit. Here we will basically concentrate over the 32-bit version. These are the parameters which we have to apply if we want to generate the numbers for the MT19937. The speciality of this Mersenne Twister, version is it has, or any Mersenne Twister is the twist and tempering function. Twist is a little bit complicated function. I'm not going to talk about twist right now, but temper is very easy function. You see, the tempering function is something like this, which is only solve, shift, and add. There is nothing else here. And this tempering function basically tempers the bits in such a way that they have just simple recurrence relation. By using this relation, we can create random numbers which are very popular, and we will see that it actually satisfy lots of tests. Now, this is the working principle of Mersenne Twister. It takes a 32-bit seed. It initializes the first state 0. So, while initialization, it will this first 624 words will not be used for generating random number. After that, twist function is applied. Then we'll get the first state set. This state set will contain 624 into 32-bit. So as we are generating 32-bit numbers, so one array will be given as the first random number, but it will not be given directly. Before that, this temper function will be applied. If we want to say 4 random numbers, so after we have applied twist for the state 0, from this state 1 itself, we can directly get 4 random numbers by applying tempering function 4 times. So once these 624 numbers are exhausted, then only again the next state will be generated, and at that time twist will be again pulled up. So this is the way Mersenne Twister works. At a time, it creates 624 32-bit numbers, and also it uses 624 words to store those numbers. Mersenne Twister has certain limitations. First limitation is it is not cryptographically secure because the twist function is not one-way function. Second is it has a zero-access initial state problems that will continue for more than 10,000 generations. What is this problem? That is basically if the seed has the seed contains more number of zeros. In that case, that zeros will be continued for more than 10,000 generations. After that only we can get really random number. So that is a zero-access initial state problem. And it needs really large space. Internal state is 19937 bits, which we have to store everything. There is certain variations that were also proposed. First one is SFMT, single instruction multiple data, SIMD oriented first Mersenne Twister. It has all the features of MT along with the multi-stage pipelines and single instruction is multiple data SIMD feature. And the popular one is also having the same period, that is 2 to the power 19937. That is called SFMT 19937. There is another version also, which is having lesser period and smaller internal step, but it is not that much strong. Here the period length is 2 to the power 127 minus 1, so internal state requirement is only 127 bits. Now, why we went for this emulating Mersenne Twister using CA? The reason is, if we look about the status of the CA-based PRNGs, here we during my PhD we did such a survey. Here, if you see that these are the CA-based PRNGs. If you consider the rank of these PRNGs are pretty low. If you don't consider the decimal CA and root 30. This rule 13 is the implementation, not exactly the implementation of rule 1, but here only one bit out of the configuration we can take. So it is not very practical to implement. And decimal C also has a problem of, has a limitation rather, that it can't be implemented on hardware. Other than that, this is the status of the existing CA generators. So our thinking was that why CA is not performing that much good, whereas the machine twister, which is a simple LFSR having a recurrence relation, is performing so well. So why not we just emulate it with a good CA and see how far we can get. Therefore, our objective is we want to emulate the machine twister 19937 using CA while trying to outperform it in terms of space, speed, and randomness. We took one special CA which was introduced in this paper, Imperfect Strategies to Generate Primitive Polynomials over GFT. Here, one special CA was introduced, CA 150-, which has rule 90 at the first cell, and all other cells are containing rule 150. So it is a linear non-uniform CA, and with non-uniform CA which has 90 or 150, that can only be maximal length, linear maximal length CA. So this CA has the potentiality to be a maximal length CA. And in that paper, they have shown some strategies and some experiments where this table I have taken from their paper itself. So where you can see that for most of these lengths, this CA is actually a maximal length. Here the star marks for positive. So apart from those marked as star, all these lengths are having maximum lengths. Also, they talked about one conjecture just before this sir was talking about conjecture, hypothesis, antithesis. So they have said one conjecture that CA 150- will have maximal length if the CA size A is a Sophie-Germain prime. What is a Sophie-Germain prime? Sophie-Germain prime is if n and 2n plus 1 both are actually prime. If you observe this table, you can see that for all such n's, the CA is actually a maximum CA. So we can consider that this conjecture is probably true, and we can proceed. In this paper, we have considered that. Now our task is we have to find the perfect length of the Sophie-Germain prime using CA 150- that can be a good PRNG for us. Now we want to emulate machine twister. Machine twisters period length, that machine prime they have taken, that is of the form of 32 cross something plus 1, and the cross something is the number of random numbers that we can generate together. So we want to stick to that form, and we want our Sophie-Germain prime to have this form, that is 32x plus 1, and we tested over the range of 1 to 20,000. Also, we have to consider that this length is not very large. We don't want our PRNG to store 19937 bits at every time. We want to have it smaller size, but it should be, the period length should be enough so that it can't be exhausted. This was our target. Now, we can't explore the total state space or configuration space of a large n like this. So how can we do that? We took up a British strategy. We used this information that CA 150- is reversible for any n except this, and we took this strategy. We first checked whether this all zero forms a single length cycle, and whether for any other configuration, any other initial configuration, we can get back that configuration within this 10⁹ iterations. So that was our strategy. With this strategy, we just ran our this is a table which shows some examples for the smaller sizes. You can see that when this bold are the maximum lengths, you can see that 11, 5, 23, these are the Sophie-German types. And for them, the observed cycle length is actually maximum. So this C is a maximum length. Finally, we choose N as 1409. This is a Sophie-German prime of the form 32 into 44 plus 1. That is, every single configuration will produce 44 32-bit random numbers, and the period length is supposed to be 2 to the power 1409 minus 1. So it is a good space-time trade-off as well as huge period. Now we want to look in more details to the PRNG. We see that if we look inside the PRNG, it has some if we just take the CA as it is, there is some triangular patterns inside it, which is not good for a random number generator. So we have to remove these patterns. Now we use the same technique that was used by the Mersenne Twister. We use tempering. That will improve the K distribution to 32-bit accuracy. And we took the same function as the Mersenne Twisters. So this function I have written here again. This is same as the Mersenne Twister function, but we have used some different parameters. These parameters we have found by experimentation. Now, how we can judge whether the generator numbers are good enough? There should be some metric. We have used the standard test beds available today. That is, first is Dieharder, which contains 114 tests. Then test U01 big trash battery, which contains 106 tests, and NIST, which contains 15 tests. These are the standard tests available for judging the randomness quality. To check whether the PRNG works or not, we need a seed, but still now we have not considered what can be our seed. So to find the seed, we again ran a program. That is, we took 100 seeds using RAN, but we considered some features to be satisfied for each of these seeds. We have to make sure that the seed generated has number of zeros and ones equal. There should not be any series of continuous same bit, and we took 32-bit blocks with equal distribution of zeros and ones to fill up the entire loop. Then with this setup, we ran the CA and we generated a small size of 12 MB bin file for every seed and tested with Dieharder. For this small size, obviously Dieharder will fail because it works best with the more than 10 GB file size. But we considered only those seeds which has passed more than 40 tests even in this small size. Now, if we compare them, we have got that two seeds with seed number 187 and 367, because you understand that this is 1409, this is the length of the seed. So we just mean that we have given some numbers to those seeds. So these two seeds were performing very good. We took them as our seed. And we tested with test U01, NIST and Dieharder. For Dieharder, we have taken two file sizes. I will explain why it is taken. So first, this is the Dieharder result. If you see 12 GB result, you can see that for 12 GB, none of our CA as well as the competitors, Mersenne Twister, TinyMT, SFMT, none of them are failing any test. So as we are not getting any failure, we went to the smaller file size, which is 1.2 GB. And here we see that here we are getting some failure. It is failing 2. This for seed 367, it is getting failure of 1. For Mersenne Twister 3, TinyMT 2, SFMT 5. Therefore, from Dieharder we can say that already our CFS PRNG is beating all its competitors. And seed number 367, this is the best one. Now we keep on doing the other test with this as the default seed, that is the seed number 367. For NIST, we have observed that our CA as well as all its competitors are passing all the tests. But test is and big crush is left. For test is and big crush, we are not happy with the result. What we got is for SFMT and MT, linear comparison, linear complexity test is failing. Whereas for us, matrix rank test and linear complexity test, both are failing. For TinyMT, lots of tests are failing, but we can ignore this. TinyMT is not competitor to us. But here we have for our PRNG and SFMT-MT, if we compare them, our PRNG is lagging behind because of this matrix rank test. Now we look inside the what these tests signify. We have seen that these tests are basically detecting linearity in the generator. So we thought maybe as we are taking the linear CA, that might be the problem. So we plan to add non-linearity in the PRNG. There were two approaches for we took that from Mersenne Twister and we use the twist function in two different approaches. First one is twist on the output, that is the 32-bit generated. On that we are applying twist. Another is on the CA configuration itself we are applying the twist. After that we are applying the 10-bit. So these are the two processes by which we are applying twist. And another one is using basic nonlinear component like sort followed by multiply, which we can perform after twist on the output, not on the CA configuration. We have done this. Now, first we want to show the result of this twist on the application of twist. This is the basics, our basic PRNG that we have developed so far. Now we changed it to this, that is, we took the CA generation, we applied temper and twist. We check if after this, for if someone requests one number, we'll keep on generating numbers. If 44 bits are exhausted, then again we will go for CA generation, and then again we will apply temper plus twist. That is the twist on output. The next version is CA after generating the next configuration, we apply the twist. Then we keep on apply the temper over the changed configuration. Then we do the same process of generating. So these are the two variants. Now we again compare with both Dieharder and test-01. For Dieharder, we see that here only 1 is failing. Now 4 is weak. Twist for twist on output, whereas twist for here I have written state, but it is going to be configuration. For twist and configuration, 3 are failing and 9 are weak. So it is not a good result. So this one is comparable to this, although here number of weeks is larger, whereas number of week test here it is improved. So we can take that twist on output is the better version among all of them. But if we consider the big cross test, there is no improvement. It is failing the same test it was failing before. Now we add the nonlinear component, which is XOR, multiply, or SBox, but there is no improvement on result. Therefore, we by this time our PRNG itself is becoming very heavy. It is not fast because the nonlinear component is taking much time. So we propose not to use these unnecessary XOR multiply operations. Rather, we stick to the better version we have found so far. that is the temper plus twist on output with CA150 dash, where the seed is 367 and it has a period of 2 to the power 1409 minus 1 if the conjecture is true. So this is the final PRNG structure that we are going to use. But obviously you can understand that there are, these are the space-time diagrams of our generator. You can see all the generators are looking almost similar. And you can see that there are some future work to do as linearity. We have failed to improve the PRNG by using linearity and the twist and the temper. So maybe we have to move to nonlinear CA if we stick on using CA150 dash. But the problem is we still don't know how to find the suitable maximal length nonlinear CA. There might be some other CAs as well which have similar characteristics like CA190 dash, which was also introduced in the same paper. That those CAs maybe we can try to find out which can be maximal length as well as good source of randomness. But still, our PRNG, by using our PRNG, we can easily beat the Mersenne Twister 19937. It is better performing than both SFMT and MT in terms of the Dieharder. It is failing only linear complexity and matrix rank test of big trust, which takes linearity in the generator. And so for any application where linearity is not linear component is not that much harmful, we can propose to use our generator as it is going to be very fast and uses very small space in comparison to the Mersenne Twister. These are the references. Thank you.
Audience. Hello, I invite questions from the audience, please.
Nine questions, please.
Hello.
Yeah.
Any questions?
I have one question.
Yes.
Hello, please.
So, do you believe? Just a minute.
Yeah. Kamalika,
Yes.
do you believe that by adding non-linearity, you can beat the Mersenne Twister?
Mersenne Twister. Yes, we can beat Mersenne Twister, but the problem is Mersenne Twister itself, it is failing some test. So it's not about only Mersenne Twister. And if you just think like why Mersenne Twister is passing some test, but our CA is not passing that, Mersenne Twister itself is supposed to be a linear. It has the linear component. The recurrence relation is very simple and it is a linear function. But using the tempering and this twisting, if they can achieve this much good performance, so my question is whether that is only because of this long-term association or long-term dependency, which is making it better perform. Whether we can achieve that much good performance by our CA, which is having the neighborhood dependency or short-term dependency, that is the question. Otherwise, if Mersenne Twister can achieve something having the linear relation, why not CA? CA should be able to do it.
No more question from my side.
So, may I add that are you going to say that it is cryptographically secure?
No, sir, I'm not claiming that. I'm not claiming that. Mersenne Twister itself is not cryptographically secure because the twist function and tempering function are not one-way function. So as we are using the same kind of technology, I don't expect our generator to be cryptographically basically.
I have another small query.
Okay.
It looks like you have used the linear functions, right?
Yes, sir, linear function.
So,
Linear CA.
will be any nonlinear functions will be any help? What is your idea?
Yeah, that is what we are planning to do. That if we can find some non-linear maximal length CA would be the best option. If not, if we can find non-linear near maximal length CA, which is having same kind of property, then that might be a better option than this. But we want to stick to the two-step for this purpose.
Another small clarification, in the textbooks, there are certain characteristics of pseudo-random numbers. So I hope you have met all the characteristics of those pseudo-randomness.
Sir, these characteristics are supposed to be tested by the test bed. So if I am failing some tests, then obviously at least some of the characteristics we are not able to meet.
Okay.
And none of the existing PRNGs also are meeting them. That I can assure. So that is the real problem. That the test beds are more powerful than the existing random number generators.
Sure. Okay. So I invite other questions, please. I invite from the audience.
I have a question, sir.
Yes.
Hello. Am I audible?
Yes.
Hello.
Yeah, Shobhit, you're audible. We can hear you.
I think my network. I have a question that the linear maximal length here has a maximum cycle length, and also non-linear maximal length of the maximum cycle length. So rule 30, I think rule 30 is a good pseudo-random number generator, and sometimes rule 30 produce a near about maximal length cycle. So why we need this non-linear maximal length CA comparison to rule 30? That means if we believe that non-linear maximal length CA passed all the tests or near about passed all the tests, so that's why we can use the rule 30, na? It's also non-uniform and also near about cycle length of non-linear maximal length CA. So what is the difference between the rule 30 and nonlinear maximal length CA? That means why we need nonlinear maximal length CA to beat the Mersenne Twister and etc.
Okay, that is interesting. But rule 30 has some patterns. It is an established as it is already established, as Wolfram was saying, as a good source of randomness. But I didn't test the same process with rule 30. Maybe that would be an interesting thing to see if emulating the same behavior by rule 30 will give us better randomness quality. But in this work, our target was like we'll be doing the same kind of analysis just like Mersenne Twister is doing. Mersenne Twister uses a linear recurrence relation, so we'll be sticking to the linear CM. But as you were suggesting, that might be rule 30, which is a non-uniform uniform non-linear CA, and which is established already as a good source of randomness, might be that if we just do the same kind of analysis with rule 30, that will give us some kind of perspective, some kind of result. But obviously, we will not be able to meet the period length of Mersenne Twister. And another problem will be that for rule 30, there is another problem which I want to say, that is we don't know for which seat we are going to get the maximum length or the maximum possible length for rule 30. We don't have any information on that. For maximum length CA, that information is already there. So that is one facility.
That's correct. Initial configuration, but rule 30 sometimes have produced some pattern, but also in nonlinear CA we can get some type of pattern. Na? That means pattern are.
No, patterns are there. Patterns, everywhere patterns is there. That for removing patterns only, they are using this tempering and twisting these things. So after using this tempering and twisting, patterns will be removed. That can be sure.
Okay, thank you.
Yes.
Okay, if is there any other question, please? Is there any other question? So if there is no other question, let me thank the speaker, Kamalika. Thank you very much.
Thank you, sir.